Chapter 7, Section 15, Feedback Inhibition. Now, feedback inhibition you've heard in numerous other classes, cell molecular, cell biology, genetics, biochemistry, whatnot. Feedback inhibition basically means that the end product of a metabolic pathway will allosterically interfere with, inactivate, however you want to think about it, an early step in that metabolic pathway. It may not be the first enzymatic step, but it's going to be up near the front. Okay, that way you shut things down. You shut things down, that metabolic pathway no longer is making any of that end product. And once the level of that end final product drops, it's no longer interfering with those first enzyme, and then that pathway can kick off again. So we see that this interference is reversible. It's all depending upon what are the levels of that final product. High levels of product, well, then you need low levels of enzyme activity at the beginning of that pathway. Low levels of product, well, you know what? Kick it back on. Get that pathway rolling again. So it turns out one, if not a couple, of the early enzymes in that pathway are going to have an allosteric site that allows for binding of that final product. The binding will then change the conformation, change the shape, conformation, change the shape, change the function. So the final, what we see in these pathways, remember, you take enzyme A, B, C, D. A takes an initial substrate, turns it into intermediate 1. It turns out 1, substrate for B. B turns 1 into 2. 2 is the substrate for C. C takes 2, turns it into 3. D takes 3, turns it into the final. Well, that final goes back, as we see here. It goes back and will bind somewhere. Okay, because remember, allosteric inhibition binds somewhere on that polypeptide or that protein complex that is in the enzyme A. The active site changes shape because of this binding, this allosteric binding of a final product. Notice the active site here changes shape. It no longer is the correct shape for the initial substrate to enter into. High levels of that final substrate, low levels of enzyme activity. It's not completely shutting it off, because as long as that product is high levels, it's going to be there. But when that product level drops, it's not interfering now. Now you're going to get activity of that enzyme. That enzyme now has the right shape to active site to allow for entry of the substrate and for it to be acted upon. Cut, paste, twist, tweak, whatever. We also see, though, that it's not always so cut and dry. You see enzyme A takes substrate, turns it into intermediate 1. But what happens, though, if there's numerous substrates that can be turned into intermediate 1? Here, DAHP is an example. You have 3 enzymes, and I'm not going to go over which 3 are. Now, I don't care what those 3 are. Just here in our example, there's 3. 3 what they call isoenzymes. 3 enzymes that can do roughly the same thing. They take a substrate, but they all turn it into a product, DAHP. Here's the kicker. Those 3 isoenzymes are not the same protein. They work slightly differently, but they just perform roughly the same thing. Well, anything that's going to bind to isoenzyme 1 allosterically may not be able to bind and interfere with 2 or 3. So we come to find out DHAP is part of a metabolic pathway. It's going to give you charismate and charismate through different metabolic processes. Gives you tyrosine, phenylalanine, or tryptophan. These are our final products. Tyrosine allosterically inhibits isoenzyme 1, whatever that is. Phenylalanine inhibits 2. Tryptophan 3. Thing is, if all the charismate gets turned into tryptophan, tryptophan is not going to have any High levels of tryptophan is not going to have any effect on 1 and 2, but it will interfere with 3. High levels of phenylalanine has nothing to do with, activity of 1 and 3. High levels of tyrosine has nothing to do with activity of 2 and 3 here. So, turns out these isoenzymes have evolved. The cells have evolved with these isoenzymes so that the different final products will interfere with a different version of a different isoenzyme. The theory is that if you have high levels of all of them, all 3 will be shut off. But if you have low levels of 1 and high levels of the other 2, they'll shut off 2 and you'll get a reduced level, a reduced activity through that pathway, maybe ultimately leading to increased levels of that first one.